Okay, guys, welcome. Today we're going to talk about solving exponential and logarithmic equations. And we're basically just we'll go through some of the rules that we're going to need, and then we're going to go through a bunch of examples. Now, some of the rules that we'll need are given here, right? So these first two rules are going to help us solve exponential equations. And really, we are going to use basically property B. And that essentially is saying that if you have two expressions with the same base that are equal, then their exponents would then have to be equal, right? So if you have a to the x is equal to a to the y, then that indicates that your two exponents have to be equal, right? And then similarly, in these other two, these are what we'll use to solve logarithmic equations, and really we'll use property D, and that says that if you have log of something is equal to log of something, then the two somethings, in this case x and y, would have to be equal. Now, first we're going to talk about how to solve an exponential equation. And what we're going to do first is we want to try and write both sides using the same base and then use some properties of exponents to solve this. Now, it's not always possible to do this, and we'll see an example like that in a second. And then in that case, you would have to use logarithms. But let's take a look at an example. Okay, so in this first example, we have 81 to the x is equal to 3. Now, if possible, we would like to try and write both sides usually as a power of the smaller number, or sort of the closer to like our first power number, right? So if possible, we would like to write this with both sides having a base of 3. And of course, now the right side is already 3, so that's just 3 to the first. Now, can we write 81 as a power of 3? Well, if you think about it, of course, the answer is yes. So if you have 3 squared, that's 9. 3 to the third would be 27. And then 3 to the fourth will indeed give you 81. So we can think of 81 as 3 to the fourth. So that's what we're going to put here. So now we use our power to a power rule, and we can write the left side as 3 to the 4 times x is equal to now 3 to the 1, which we didn't change. All right, now we can use that property that we just talked about earlier that says if you have a to the x equals a to the y, in this case, these are like our x and our y. So we have 3 to some power is equal to 3 to another power. And if that's true, that really means that those two powers need to be equal. And of course, we can solve this fairly easily. We could say that x is equal to 1/4 from here. All right, so that's the first example. Now, in the second example, we're not quite as lucky, right? Because in this case, we can't write, so the left side would be 3 to the n, but we can't write 26 as 3 to some number, right? So 26, we can't write as 3 to some power. So we need to use something else. So we cannot write both sides as a power of 3. So we need to use logarithms instead. Now, it turns out that if we convert this to logarithm form, well, I'm going to have a log base 3, right, of 26 is equal to n. All right, so as long as we can figure out how to find log base 23 of 26, then we're in good shape. Now, one thing that's not mentioned in this section of the textbook that we're going to need, that I'm going to mention now, but we also are going to talk about a little bit in a future video, is what's called the change of base formula. And this is going to allow us to find, for example, these logarithms that are not a common log or a natural log, which we haven't talked about yet, but we'll talk about later, in our calculator. Because if you look on your calculator, you're not going to find anywhere to enter in a log with a base of 3. Right? So to get around that, what we're going to do is we're going to introduce the change of base formula. And this says that if you have log base a of b, you can write this as a common log of b over a common log of a. Right? So that's what we're going to do here. So to get n, we could say that this is a common log of 26 over a common log of 3. So now we just enter this into the calculator. So if we find log of 26 and we divide that by log of 3, then we get that n is roughly 2.9656. Again, I should say this is approximately equal. All right, so now in this case, we couldn't write both sides using the same base. So if that happens, you need to use logarithms. All right, so in this case, when we did that, we needed to change a base formula, and that allowed us to get our n value here. Okay, now the next example, we're going to solve a logarithmic equation. All right, now in this example, there's really 2 ways that we can do it. So one way is to first convert it right away to an exponential form. Okay, and if we do that, this says that we have 3 squared is equal to x minus 1 to the 4th. All right, now the problem is that this is going to be annoying to FOIL out. You could do it, but it would be annoying to distribute. All right, so we're going to do it a better way. And we're first going to simplify using our log properties. Now, if we do that here, of course, we could use the power rule. And we could bring the 4 out front, and then we have a 4 log base 3 of x minus 1 is equal to 2. Right? And now we can divide both sides by 4, and then we get a log base 3 of x minus 1 is equal to 2 over 4, which we can reduce to 1 over 2. So now if we convert this to exponential form, we get 3 to the 1/2 is equal to x minus 1. And we know that 1/2 power is the same as a square root. So this is square root of 3 is equal to x minus 1. So last but not least, we can add 1 to both sides. And we get that x is equal to 1 plus square root of 3. All right, and if you like, you could get a decimal approximation for that answer, but here 1 plus square root of 3 will do the trick. All right, so hopefully that is not too difficult. And again, the idea is that we can use our properties of logs to make this a much easier problem, right? Because now if you were to just use this form, you'd have to essentially find the roots of a 4th degree polynomial, right? Which is, or I guess you could even take the 4th root of both sides, and that would probably be the easy way to do it. All right, but then that would be similar to the other one. Okay, so now we have an equation that strictly has logarithms. All right, now the problem is that we have two of these on the same side. So what do you think we're going to do? Of course, we're going to combine these. So anytime you have a logarithmic equation, the first thing that you want to do is you want to combine all logs on each side. So on the left side, of course, we can combine them using the product rule, and we can say that this is a log of 3 times 2x plus 1. And then that's equal, I'll put this in black since I didn't change it, a log of 5x plus 8. All right, well, now we have log of something is equal to log of something. So that means that these two somethings really better be equal. So we can say that 3 times 2x plus 1 had better equal 5x plus 8. Well, now this is something that we can solve fairly easily. If we distribute here, we'll get a 6x plus 3 is equal to a 5x plus 8. So now we can bring our x terms to one side. And I'll bring this 3 over to the other side. So these cancel and these cancel. And we're left with x is equal to 5. All right, now when you solve a logarithmic equation, you need to check one final thing. We now need to check, need to make sure our x values do not result in a non-positive logarithm. Right, so any x value that we find, we need to make sure that that doesn't cause a negative value or a 0 value inside any of our logarithms. But of course here, if you plug in 5, you're going to get log of 11 plus log of 3 is equal to log of 33. And all of those numbers are positive, so that's good. All right. If one of these, if we had an x value that resulted in a negative number, we would throw that out. All right, so that's the idea here. Okay, let's look at another example. So again, we are in a situation where we need to combine these two logarithms. And we'll have a log of x times x plus 3 is equal to log of 28. All right, but again, we now have log of something is equal to log of something. So we can say that those two somethings are equal. So now we can distribute, and we'll have an x squared plus 3x is equal to 28. So with a quadratic, I want to move this 28 over. So now we have x squared plus 3x minus 28 is equal to 0. Now, of course, we want to try and factor this, and of course we can. So we need two numbers that multiply to negative 28, but also add to a positive 3. So those two numbers would be plus 7 and minus 4. So this tells us that x is equal to negative 7 and x is equal to 4. All right. Now, of course, we need to check these. Right. Now, if we plug in 7, we have or negative 7, we have a problem right away. If x is negative 7, then we get log of negative 7 plus log of negative 4 is equal to log of 28. All right, but these two negative numbers here are no good. These are bad. So we throw out x equals -7. So this is no longer a solution. All right, now if we check x equals 4, then we get log of, let's see, log of 4 plus log of 7 equals log of 28. And this is fine. So in this case, x equals 4 is the only surviving answer because that doesn't cause any logarithms to be non-positive. All right, so that's one thing that you have to be careful of. Okay, let's look at one more example, and I believe the next example is a word problem. Yeah. Okay, so again, we want to combine our two logarithms in this case. Now, in this one, when we combine them, we'll have division this time. And the right side is still just 1. Now, in this case, we don't have logs on both sides. So instead of saying we have log of something equals log of something, now we're just going to convert this to exponential form. So if we do that, if we don't see a base here, remember that is where we assume that we have a common log. So we can say that we have 10 to the first is equal to 8x minus 11 over 3x. Right, and of course 10 to the first is just 10, so we really have 10 equals 8x minus 11 over 3x. Well, so to solve this, we would multiply both sides by 3x, so we're going to get 30x is equal to 8x minus 11. So let's subtract our 8x from both sides. And we get 22x is equal to minus 11. So then if we divide by 22, we get x is equal to minus 1/2. Now, of course, we need to check this. So if we plug in minus 1/2, we're going to get a log of, so let's see, negative 1/2 times 8 is a negative 4, minus 11 is negative 15. All right, so right away we have a problem, but for completeness, let's just check the other one. If we multiply 3 by negative 1/2, we're going to get a log of, let's see, what, a minus 3 over 2. Right, but of course, since these two are negatives, this is not good. So we throw out our x is equal to 1/2. So since we've thrown out all of our answers at this point, we can conclude that we have no solution. All right, if we had answers left over, we could of course test them, and if they survived, we would have an answer, but since we have just one possible answer and it doesn't work, this is an example of where we have no solution. Okay, one last example in this video. Here we'll do a word problem. So in this case, we have 1,000 bacteria in a culture, and the number of bacteria doubles each hour, and the number of bacteria after t hours can be found by this formula: n equals 1,000 times 2 to the t. Now, in this case, we want to know how long will it take for the culture to grow to 12,000 bacteria. Now, if we want to know how long something will take, that means that we're interested in our t value, right? So what we're really solving is we know that it's going to grow to 12,000. So we're solving 12,000 is equal to 1,000 times 2 to the t, and we want to solve for t. All right, so how do we do this? Well, first we'll divide both sides by 1,000. All right, so if we do that, then we're left with 12 is equal to 2 to the t. All right, so now if we convert this to exponential form, or sorry, to logarithmic form, we're going to have a log base 2 of 12 is equal to t. And of course, here we just need to change a base formula again. Oops. So if we apply that, of course, again, just as a reminder, the change of base formula says that we have log base A of B. You can express that as common log of B over common log of A. So that's what we're going to do here. We're going to say this is a common log of 12 over a common log of 2. And that will give me my t. So now if we evaluate this in the calculator, we have a log of 12 over a log of 2. And that's going to give us that t is roughly 3.585. So it's going to take about this many hours to grow to 12,000. All right, so that's the solution to this word problem. All right, so that concludes this video on solving exponential and logarithmic equations. I hope you enjoyed, and I will see you next time.